Not another manual file copy.
Let me help you with MLOps.
Hi, good morning. Ali, Gaze, and I are going to talk about the diabetic patient readmission prediction using MLOps. Our project focuses on predicting 30-day hospital readmissions for diabetic patients using an end-to-end MLOps pipeline built on AWS SageMaker. Readmissions are costly and often indicate that patients need additional follow-up care after discharge. By identifying high-risk patients early, healthcare providers can take preventative actions such as scheduling follow-up visits or adjusting treatment plans, ultimately improving patient outcomes and reducing avoidable healthcare costs. We use the UCI Diabetes 130 US Hospitals Dataset containing over 100,000 patient encounters and formulated the problem as a binary classification task where patients readmitted within 30 days are labeled as positive and all others as negative. Beyond building a predictive model, our goal was to demonstrate a complete production style MLOps workflow, including data engineering, model training, deployment, monitoring, and CI/CD automation. The system architecture begins with the UCI Diabetes readmission dataset, which is stored in Amazon S3 as the central data lake. The raw data is uploaded to S3, then processed in SageMaker notebooks where we clean the data, select features, encode categorical variables, and create the training, validation, test, and production datasets. For model development, we use SageMaker to train and evaluate machine learning models, including and an XGBoost model. The models are then compared using accuracy, precision, recall, F1 score, and ROC AOC. Since this is a readmission prediction problem, recall is especially important because we want to identify as many high-risk patients as possible. Based on Ali's implementation, the deployment workflow is designed. The trained model can generate predictions on the production holdout data stored in S3, and the prediction results can be written back to S3 for reporting, monitoring, and future integration with hospital decision support systems.
So we began by performing exploratory data analysis on the diabetes readmission dataset. This contained over 100,000 hospital encounters. The goal of this phase was to better understand the data before building any machine learning models. We examined the distribution of the target variable, which is whether a patient was readmitted within 30 days, and found that readmissions were the minority class, indicating a class imbalance problem. Then we also explored demographic and clinical features like age, race, gender, previous hospital utilizations. One of the trends we observed was that readmission rates generally increased with age and with the number of prior inpatient visits. This analysis informed our feature engineering strategy. After understanding the data, we then focused on data engineering and feature engineering. From a data engineering perspective, the raw data set was uploaded into Amazon S3, which served as our data lake. Then we created an Athena database, an external table. This allowed us to run SQL queries directly against the data stored in S3. This helped us with validation, exploration, and data quality checks. For feature engineering, we first converted the original readmission categories into a binary target suitable for classification. We also removed identifiers that did not provide predictive value. Since many variables were categorical, we applied one-hot encoding to transform them into numerical features that the machine learning algorithms can process. Then we cleaned and standardized feature names to ensure compatibility with SageMaker services. So the result was a clean and structured data set that could be consistently used for training, validation, testing, and monitoring throughout the MLOps workflow. And then to satisfy the feature management component of the project, we also demonstrated SageMaker feature stores by creating a feature group for the engineered diabetes features. This allowed us to show how features can be centrally managed, versioned, and governed within an MLOps environment. However, it is important to note that feature store was not actually used as a part of our training pipeline. Since the dataset was static, we only have one model. So here the feature store added complexity without much benefit. Instead, our production workflow used the processed dataset stored in Amazon S3 as a source for model training and evaluation. The feature store portion was included primarily to demonstrate feature management concepts, and it showed how engineering features could be organized and then reused in a larger enterprise MLOps environment.
In the early exploration phase, we compared logistic regression as a simple baseline with XGBoost. Logistic regression helped us understand the basic benchmark, but for a final automated pipeline, we selected XGBoost because it performed better overall and works well with structured healthcare data. So in the final SageMaker pipeline, the training step is focused on XGBoost. After training, the model is evaluated automatically and the metrics are saved into an evaluation.json file. Here the model achieved about 75% accuracy, 38% recall, and 25% F1 score, and 64% are OCA-UC. Since this is a healthcare readmission problem, recall and F1 are important because we care about identifying patients who may be readmitted within 30 days. The F1 score is also used as a pipeline quality gate. If the model meets the threshold, the workflow continues to batch inference. If it doesn't, the pipeline fails safely instead of pushing a weak model forward. So the main point is not only the model score, but that the model training, evaluation, and release decisions are automated and reproducible inside the machine learning operations pipeline. This is the automated SageMaker pipeline that orchestrates our workflow. It performs preprocessing, model training, evaluation, model registration, and we have batch inference. And we also implemented a quality gate using an F1 score threshold. If model passes the threshold, like this pipeline, batch inference executes automatically. If it couldn't, the pipeline enters a failed state. This demonstrates CI/CD controls and automated model validation. After a successful pipeline execution, the train model artifact is stored in Amazon S3, and evaluation reports are also preserved for reproducibility. The pipeline then runs batching transform to generate predictions on new patient data. These prediction results are written back to S3 and can be consumed by downstream healthcare systems. Here we can see that we also implemented monitoring using CloudWatch, that after evaluation, the pipeline publishes performance metrics, including accuracy, precision, recall, F1 score, and any other metrics that we want to have. These metrics are visualized in a dashboard and provide operational visibility into the machine learning workflow that is really practical, can be used by the different roles of the company. Now we want to have a live demo navigation. This is what I would actually show. First is the pipelines that we can find it in Amazon SageMaker. In SageMaker Pipelines, we have multiple pipeline here. That this one that was stopped in 3 seconds because of a problem in code, and this one was failed because of a threshold F1 score. And this one could pass the condition and batch inference executed. Here's 3. We have here pipelines, batch transform outputs that show the result, and we have model artifacts here for this specific pipeline. In output we can find the tar file, and the workflow also publishes performance metrics to CloudWatch for monitoring and operational visibility. You can see here all metrics and choosing. To conclude, we built an end-to-end machine learning operations workflow for predicting diabetic patients' readmission. That we use AWS SageMaker. The project includes data engineering, feature management, automated training and evaluation, CI/CD automation, batch inference, and monitoring. While model performance can be improved in future, the project successfully demonstrates a production-style machine learning workflow and core machine learning operations principles. Thanks for your attention. Thanks to my teammates, and especially thanks to the professor for giving us this opportunity to present our project.